Today, we are talking about simplifying radicals and complex numbers. Okay, so first I just wanted to start out kind of by reminding us what our perfect squares are and what our square roots are. So a perfect square is a product when a number is multiplied by itself. So x times x would give us x squared, so that x squared is a perfect square. Or likewise, 5 times 5 is 5 squared, or 25. So we would say 25 is a perfect square of 5. So it is really helpful to know your perfect squares from 1 to 20, and I've listed them in this chart below. So that's kind of something I would either keep out to have refer back to while you're working, or really try to memorize it. All right, our square root. Now the square root is the inverse operation of a square, right? So I take a square root of x squared, it undoes the square and I just get the x. Or if I have the square root of 25, I know that 25 is 5 squared, so that square root undoes the square, and so it leaves me with 5. And so 5 is the square root of 25. So when you know your perfect squares, it's easy to figure out their square root. So again, I've given you a list of the table of perfect squares for you to refer back to while you're doing homework or to try to work on kind of committing to memory. Now, when we're simplifying with square roots, there are a couple properties that are helpful for us to know. There's a product property for square roots, that if I have the product of two numbers underneath a square root, I can split them into the square root of the first number times the square root of the second number. And then this also goes both ways, that if I have the two square roots multiplied, I can write them as the square root of the product of the two terms underneath one radical. And then the quotient property, that if I have a fraction underneath a radical, I can split it up into the radical of the numerator over the radical of the denominator. And again, this goes both ways. Sometimes it's helpful if you start out with a radical over a radical to simplify by putting them under one radical. Now, let's take a look at how we can use some of those to look at simplifying radicals and other operations with radicals. So when we're simplifying a radical, to simplify, you need to find the perfect square factors. Once you find a perfect square, you take the square root of that factor, and then the remaining factors stay under the radical. So when we have the square root of 75, I know that the square root of 75 is 25 times 3, because 25 times 3 is 75. So if I split it up, then I have that perfect square factor, so I put that under its own radical, and the 3 goes under its radical, and then I know that the square root of 25 is 5, and so it comes out of the radical, and then the 3 is not a perfect square, so it can stay in the radical. So this would be our final answer. Now, there are lots of different ways, and I'll show you a few examples of, if you're not sure how to find the perfect square factors, about how you can kind of break down these numbers in case you don't see the perfect square factors right away. All right, adding and subtracting radicals. To add and subtract radicals, you combine like radical terms. Like radical terms are when they have the same radicand, and the radicand is really that number under the radical. So that's what a radicand means. Sometimes you have to simplify radicals at first in order to see if they are like. So here we can see that we have 6 root 5 plus 3 root 5. So we notice that under our radicands are the same. So all we're going to do is we're going to just change the coefficient. So think of this, you could almost think of this as like 6x plus 3x. All we would do is just change the coefficient. So 6 plus 3 is 9, so we have 9 root 5s. Similarly, we can do the same thing with subtraction. Again, they have to be the same radical. So I see that I have a root 11 and a root 11. So I can just take 6 minus 4. 6 minus 4 is 2. So there is 2 root 11 left. All right, multiplying radicals. So when we're multiplying radicals, you multiply our coefficients on the outside by each other, and you multiply the radicals underneath or the radicands underneath the radical by each other. So I would have 4 times 5, so 4 times 5, and then the numbers under the radical, they would stay under the radical, 3 times 8, root 3 times root 8. So then I multiply coefficient times coefficient. So 4 times 5 is 20, and root 3 times root 8 would stay root 24. All right, now we always want to make sure that whenever we're simplifying or multiplying radicals that we check to make sure that our new radicand is simplified. Okay, well, I noticed that this does have a perfect square factor. 24 could be written as, right, we bring our 20 down, but it could be written as the square root of 4 times 6, because see, 4 is that perfect square factor. So then I've got 20 times the square root of 4 times the square root of 6. And we know that the square root of 4 is 2. And when that 2 comes out, it multiplies by what's already on the outside. And the square root of 6 does not have any more perfect square factors. So we just bring it down, and we would simplify this by multiplying that 2 that came out with the 20 that's already there. So I would have 40 root 6. Okay, and then that would be my final answer. Now, the last thing that we're going to look at is dividing radicals, which often means that we're going to need to rationalize the denominator. We can never leave radicals in the denominator. So over here, if we were given as a problem 7 over root 3, we would say this is not simplified. And so in order to simplify it, we would rationalize the denominator. To do this, you multiply the numerator and the denominator by whatever radical is in the denominator. So since we have a root 3 in the denominator, we're going to multiply the denominator and the numerator by root 3. And the reason that we can do this is root 3 over root 3 is just 1. So it didn't change the value of our fraction. So I would have the 7, it's on the outside of the radical, so it stays on the outside of the radical, and the root 3 is going to just come over and stay root 3. Now, the whole purpose of me doing this is because I know when I multiply a number times itself, it's going to give me that perfect square. So 3 times 3 is 9. And so, again, we see that the 3 up here cannot simplify, so it's going to just stay under the radical. But we know that the square root of 9 is 3, so it can come out of the radical. Now, the thing that you want to be careful about when you're looking at fractions with radicals is that I can only simplify. I see this 3 in the denominator and this root 3 in the top. I can only simplify things if they are both under the radical or if they are both out of the radical. So since this 3 is outside of the radical, I would only be able to reduce it with the 7 if that was possible. 7 and 3 do not reduce, and so this would be my final simplified fraction. Let's look at a couple of examples of this. So we see square root of 50. Now, friends, let's just say that we could not think of what the perfect square factors are of 50. If you know them, then you're going to go ahead and you're going to just write it underneath that square root and simplify it like I did in my last example. But let's say I just cannot figure out what my factors are. So then I say, all right, I'm going to break them down. 50 can be written as 5 times 10, and then 10 also breaks down to 5 and 2. So what this shows me is I have 2 5s, or I have, if I was simplifying, sorry, let me bring my negative, I would have 5 times 5, or 5 squared times 2, and now we can split that up. So I know that I have the square root of 5 squared times, sorry, I keep forgetting my negative, times the square root of 2. So the square root of 5 squared is 5, so I just bring my negative down, so that's negative 5. Root 2 does not simplify anymore, So I would just bring it down and it would stay under the radical. So my simplified radical would be negative 5 root 2. Okay, let's look at this again. So let's say on this time I've either practiced my square roots or I know my factors really well. This time I see 48. 48 has a factor of 16 and 3. So I could split this up as 16 times 3. Well, I know that our product property says I can split that into the square root of 16 times the square root of 3. I know the square root of 16 is 4. Square root of 3 does not simplify, so I just bring it down the square root of 3. And so my answer would be 4 root 3. Now again, if you weren't sure, we could simplify this by just multiplying, breaking it down, right? We would say, what do we have? We could say we had 4 and 12, and then 12 could be broken down to 4 and 3. Now, I know that these 4s could both be broken down even further, but once I have a matching set, then that would give me that 4 squared, which is what we had right there at the 16th. So again, you can, if you can't right away notice what those squares are or those perfect squares are, look for breaking it down into, kind of a factor tree so that it can help you figure out what those numbers are. Okay, now we're multiplying. So when we multiply, remember we multiply the numbers on the outside times the number on the outside and the number on the inside with the number on the inside. So outside we have 2 times 5 is 10. And then we look at it and we say, okay, 3 times 12, that's 36. And then we notice that 36 is a perfect square. 36 is just 6 squared. So then the square root of 36, or 6, would come out, and it would multiply with what's already there. So 10 times 6 would be equal to 60. So 60 would be my simplified answer. Okay, so over on the other side, we talked about that sometimes when you have square roots that are divided, it's helpful to have them split up like this. But sometimes it can be helpful to put them under one radical to see if they simplify. So if I write this under one radical, 200 over 8, and then I notice that 200 over 8 does simplify, it reduces to 25. So this becomes the square root of 25, and I know the square root of 25 is just 5. So that makes it a lot easier instead of having to rationalize that denominator. Okay, now looking at number 5, I see, well, square root of 5 and square root of 7, those do not simplify. So the only way to simplify this is, remember, we cannot leave a radical in the denominator, so I need to rationalize that denominator. Now remember, I multiply the top and the bottom by whatever the radical is in the denominator. So root 7 over root 7. Then I multiply, my coefficient doesn't have a coefficient to multiply, so it just comes out. And then I have root 5 times root 7. So 5 times 7 is 35. And then that root 7 times root 7 gives me the square root of 49, which is just 7. And then I would want to check and make sure that 35 can't be simplified anymore. I already know that 35, the only factors are 5 and 7. Neither one of those are a perfect square factor. So this is my final answer. All right, number 6. So again, we look at number 6 and we see a 5 over a 10 and we really want to reduce it. But remember, we cannot reduce here because the 5 is on the outside of a radical. It's not under a radical, and the 10 is on the inside. So the only thing we can do here is just rationalize our denominator. So multiply by root 10 over root 10. So I get 5 root 10. And guys, if you notice, the whole point of multiplying the root times itself is because it gets us, it's that kind of 10 squared. So if you want to skip the step of saying that this is the square root of 100 and just jumping over to a radical times itself will always just be the number underneath the radical, because that is basically like saying we have the square root of 10 squared, and 10 squared would just be 10. So you can kind of skip that step. Now here, again, I see the square root of 10 under there, 10 under the radical and 10 out of the radical, so I cannot reduce those, but 5 and 10, these are both outside of the radical, and I can reduce that. So I know 5 and 10 can both be reduced by 5, so I get 1 over 2. So then my simplified radical is the square root of 10 over 2. Okay, now I'm looking at adding or subtracting radicals. So the only time I can add or subtract radicals is if they are the same radical. So because these have the same radicand, the 2, then I can just add the coefficients. So 5 plus 3 is 8 root 2. And that is as simplified as it gets. All right, and now we have root 2 minus root 3. Now, my radicands are not the same, so we can't go any further. This is as simplified as it gets, so we could just say not possible to simplify anymore. For our next one, when we look at it, we say, well, we don't think that they look like they're like terms, right? They don't look like they have like radicands. But I do notice that the square root of 80 can be simplified. So I know the square root of 80, I could think about it. And again, you can show that tree if you want to, or you can split it up into the roots. I see that it is 16 times 5, and I know 16 is a perfect square. So the square root of 16 is 4, and then we would have that 5 underneath the radical. So square root of 80 simplifies to 4 root 5. And then we have minus 5 root 5. Now they have the same radicand, so we can combine. And remember, when we're adding and subtracting, we're only changing the coefficients. So 4 minus 5 would give me negative 1, or I could just say negative root 5. Either one of those would be okay. Okay, same thing with our number 10. Again, we look at it and we say, well, these aren't the same. They're not the same radicand. But we would want to look and see if we could simplify. So again, I'm going to show it a different way, right? I know that 75 could be split up into 25 and 3, and then I have plus. So let's see, 27, the perfect square factor of 27 would be 9 times 3. And then remember, we can kind of split that up, or we don't have to show that step. We know what the square root of 25 is 5. So we have 5, and then that 3 will stay underneath the radical, plus, and then we have the square root of 9, which we know is a perfect square, and that's 3. So 3 root 3. And again, now that we've simplified the radicals, they have the same radicand, and I can combine them. So I have 5 plus 3 is 8 root 3. Okay, next we're going to look at imaginary numbers. So remember when we talk at the beginning of the year, we kind of talk about all the different types of numbers, and you hear teachers broadly say the real numbers or whatever, and you kind of always wonder, what is a non-real number? Well, a non-real number is an imaginary number. An imaginary number is it's represented by the variable I, is a non-real number that is the square root of negative 1. So if we have the square root of negative, any square root of a negative, we can now simplify and say that it is I as the square root of a negative. Now, imaginary numbers are often paired with real numbers, and we call that a complex number. And again, complex numbers are in the form a plus bi, and they're used to describe zeros of quadratic functions that have no real zeros. So a is the real part and bi is the imaginary part. So remember when we'll be talking more about non-real roots in the next day or so. Then we also know that the powers of I go in a cycle of 4. To simplify an imaginary number, you take the exponent of I and divide it by 4, and whatever the remainder is when you divide by 4 is the power of I. So these are kind of they go in cycles. So once I get to I to the fifth, it's just basically I again. So I have I is the square root of -1, which we usually just call it I. And then I squared is -1. I to the third is -I. And I to the fourth is 1. So this little thing right here, these 4 terms, you really need to have memorized, okay? So I put a little star by this and remind yourself you need to memorize these. All right, so now let's look at the example of what we would do. So we have I to the 27. So I to the 27 is some kind of power, it's one of these. And so we take our 27 and we divide it by 4. Now this is going to take you back kind of a ways to remember dividing with remainders. So I know that 24 goes into 27 6 times, right? Because I said 24. Sorry, 4 goes into 27 6 times. That's 24. So then it would have a remainder of 3. Now, I don't care about how many times it goes in. All I care about is the remainder. So I to the 27 is the same as I to the 3. So we would just say it's -I. So the answer there would be -I. Now, you will use this term, the complex conjugate, when we simplify, and you'll see it come up in an example in a second. But the complex conjugate of a plus bi is the number a minus bi. So notice the only part of it that changes is the sign on your imaginary term. To find the complex conjugate, you keep the real number the same, exactly the same, and you change the sign of the imaginary number. You will need complex conjugates when you simplify fractions with complex numbers. So up here, we talked about we had 5 plus 3i, so the complex conjugate would just be 5 minus 3i. So notice the real parts did not change. I only changed the sign of the imaginary part. So let's look at some examples of how we will use imaginary numbers. So previously, whenever we came across the square root of a negative, we just said it was not possible, but now we have the tools and it is possible. So anytime you have a negative underneath the radical, you know an I is going to come out. So if we think about this and say, well, we could split this up into the square root of 9 times the square root of -1. Well, we know the square root of 9 is 3. So remember, when things come out, they multiply with what's already out there. And the square root of -1 is just I. So this would simplify. 3 times 3 is 9, and then we'd have an I. So 9I would be the simplified radical. Sorry, this is a mistake. Let's take away that. Just a typo. Apologies. So again, we look here and we say, okay, 45 is not a perfect square, but we know that we can break it down. So we bring our 2. We think about, okay, what perfect square factors does 45 have? Well, 45 I can think of as 9 times 5. So I have the square root of 9 times 5, and then we're going to say times -1. So we can split that up. We know we have 2 and then square root of 9 times the square root of 5 times the square root of -1. Now again, guys, this step isn't necessary if you don't need to show it, if you can kind of figure it out from up here. This is just kind of getting everyone to understand like how we're actually doing this. When we split them up, they can split up like this because of that product property. So again, whenever things can simplify and come out, they multiply with what's already out there. So the square root of 9 is 3. Now our 5 is going to stay under, but the square root of -1 will come out and be I. And then we just leave. Our square root of 5 does not simplify, but we can multiply all this. So 2 times 3i is 6i root 5. All right. Just happened to notice that all mine have the same square root factor. All right, when we look at 54, we think about what we can break down there. Again, I happen to notice that it is 9 and 6. So I promise not all square roots are 9s, but they happen to be today. So we have our -1 times our 9 times our 6. So we can go ahead and simplify. We leave our fraction out there. The square root of -1 is I, times the square root of 9 is 3. And then the square root of 6, that's a 2 and a 3, so it does not break down anymore. There's no more perfect square factors. So then I have -1/3 I times 3. Well, -1/3 and 3 will cancel each other out to just give me -1. So I have -I root 6 in my final answer. Okay, now simplifying our powers of I. So we talked about it in our example a second ago that every single time you're going to divide it by whatever the exponent is. So I'm going to take 23 divided by 4. So think about it. Okay, 4 goes into 23 5 times. That's 20. So it has a remainder of 3. Now again, remember, I don't care about the 5. I only care about the remainder part. So I to the 23rd is the same as I to the 3rd, which is -I. So -I would be our answer, our simplified answer. So I to the 32nd. So again, we take that 32 divided by 4. This one actually comes out evenly. We get 8 and no remainder. So when it divides evenly, then that means it is the same as the power of I to the 4th. When there's no remainder, it's I to the 4th, and that is just +1. Because remember, I squared is -1, so I to the 4th would be -1 squared, which would be 1. All right, our last example of powers of I, we're going to take our 101 divided by 4. I know 4 goes into 101. It goes in 25 times with a remainder of 1. So again, don't care about the 25, only care about the remainder. So that's I to the 1, which is just I. All right, now we're going to look at finding the complex conjugate. Now remember, the complex conjugate, I keep the real number the same, and all I do is change the imaginary part. So my 9 stays the same. My imaginary term was negative, so I'm going to make it positive. That's it. Now, for number 8, excuse me, I don't have a real part. So the real part is kind of just 0, but I do still need to change the sign of the imaginary part. So it would just become positive for I. Okay, now remember that all imaginary terms all complex numbers are supposed to be in that A plus BI form. Now notice that this one is out of order, and you do need to check for that because a lot of times we'll forget and we'll just change the sign in the middle, but it has to be we change the sign on our imaginary term. So first we're going to go ahead and write this in the correct order. So √3 is our real part. The sign on I is still plus. So my complex conjugate, I'll leave the √3 part the same, and then I just make it a minus I. All right, so simplifying with complex numbers. So when we're adding and subtracting, you just consider them like terms. You have your real numbers that you can combine, and you have your imaginary numbers. So first of all, when I'm subtracting, I notice that I need to distribute this negative. So I have 14 minus 2i. The negative will distribute, so it'll be minus 23 minus 6i. So now I'm going to combine my 14 and my negative 23. 14 and negative 23 is -9. Negative 2i minus 6i is minus 8i. And that is my simplified complex number. All right, very similar when we're adding. Now, when we're adding, we don't actually have to distribute, so we can just go ahead and start at this point by combining our like terms. So 3 plus 7 is 10, and 2i minus 4i is going to give me -2i. All right, multiplying. Now, when we're multiplying these, we treat them just like they're a regular binomial with a variable. We just have a couple little things that we do at the end if we end up with an I squared. So we're going to distribute this 3i, and it's going to go to both terms. So 3i times 2 is 6i, and 3i times negative 2i is negative 6i squared. Okay, now guys, remember, if we remember that pattern, we have I to the 1 is just equal to I squared is equal to negative 1, I to the third is equal to negative I, and I to the fourth is equal to 1. This is the part here we want to pay attention to. Anytime I have an I squared, basically I want to cancel it out and change the sign in front of it. Because what really happened there was that this 6i was the 6i, and then the 6, and we said, well, we can simplify that I squared to make it a negative 1. Sorry, and this was minus. So we would have 6 times negative 1 would make that negative 6. So usually you'll always just see me cross out the term and change the sign in front of it. So we would also want to put this in complex number form, a plus bi. So our negative 6 will come first, because the negative times the 1, the 6 times the negative 1, and then we'll put our imaginary term next. All right, anytime we have a parentheses squared, remember we can't, if there's addition or subtraction, we cannot just distribute the square. We have to write it as, just rewrite the parenthesis 2 times. And then we know that whenever we have a binomial times a binomial, we FOIL. First, outer, inner, last. So 2 times 2 is 4. 2 times 3i is 6i. 3i times 2 is 6i. And then 3i times 3i is plus 9i squared. Okay, so remember I just told you, every time I see an I squared, I'm going to cross it out and change the sign in front of it. Okay, so now I need to combine my like terms. So I have my real numbers. I have 4, and now I have this negative 9. So 4 minus 9 is negative 5, and then 6i plus 6i is plus 12i. Okay, now here is why we talked about the complex conjugate. When I have complex numbers in a fraction, we talked about earlier that whenever we had a radical in the denominator, let me slide over here. Whenever we had a radical in the denominator, the way that we would get rid of the radical is by multiplying it by whatever that radical is, and we call that rationalizing the denominator. Well, here we have a similar process, but we can't just multiply by the same thing because it won't get rid of the I. So what we do here, whenever we have a complex number divided by a complex number, we multiply the top and the bottom by the complex conjugate. And now the reason that we do this is that it will get rid of the I terms. They'll go, the outer and inner part will cancel out, and then we'll have an I squared, which we can just change to a negative. So that's the reason that we use the complex conjugate. Now, again, we've got to FOIL these. So we're going to FOIL our numerator. So 2 times 1 is 2. Outer, 2 times 2i is 4i. Inner, 3i times 1 is plus 3i. 3i times 2i is plus 6i squared. Now I'm going to come back in a second and simplify, but I'm going to go to my bottom and do my FOILing. 1 times 1 is 1. My outer is plus 2i. My inner is minus 2i. And my last term, negative 2 times positive 2, is minus 4i squared. Okay, now what we see is the 2i and the negative 2i are going to cancel each other out. And then remember, I go back up. When I have an I squared, I cancel it out and change the sign in front. So now I have a minus. Here I'm going to cancel that out, and that's going to become a plus. So what we did, and the goal is to get rid of the imaginary numbers in the denominator, because now I only have 1 plus 4, or 5, and then it is okay to still have imaginary numbers in our numerator. So I'm going to combine my real numbers, 2 minus 6, so that's negative 4, and then 4i plus 3i is plus 7i. And then this is my final answer because I have no more imaginary numbers in the denominator. All right, so we're going to do the same process again. So we think about what is our complex conjugate. Now remember, the real part stays exactly as it is. So it's negative 5, so it stays negative 5. And I just changed the sign on my imaginary part. So I'm going to have minus 4i. So again, whatever I multiply the denominator by is what I multiply the numerator by, because this reduces to 1, so we didn't change the value of our fraction. And then I usually will put parentheses around it because it helps me remember I need to FOIL. So negative 4 times negative 5 is positive 20. Negative 4 times negative 4i is plus 16i. Negative 3i times negative 5 is plus 15i. And negative 3i times negative 4i is positive 12i squared. Okay, I'll come back and simplify that in a second. Negative 5 times negative 5 is positive 25. My 5 times negative 4i is positive 20i. And then 4i times negative 5 is negative 20i. And again, those middle terms are always going to cancel out. And then 4i times negative 4i is negative 16i squared. So 20i minus 20i goes away. We see these I squareds over here. So I can cross out this I squared and change that to a negative. I can cross out this I squared and change that to a positive. So we're going to combine our real numbers. 20 minus 12 gives me 8. Plus 16 and 15 is 31i over 25 plus 16 is 41. And again, I have no more imaginary numbers in my denominator, so it is simplified.